want this talk to be interactive as much as possible. So don't hesitate to put your questions and interrupt me while I present. So my name is Seda Shalapaicha. I'm an assistant professor of the practice at Brown University. My appointment is joined between Department of Earth, Environmental and Planetary Science and Institute at Brown for Environment and Society. And today I'm going to share my research on rethinking the spatial composite indicators with the lens of machine learning. And this is actually similar to what I've been thinking for a while, and it applied in a different context. So some of you might be even familiar with that concept before, since I introduced it previously, but now it is living in an iGuide platform, so you'll have a chance to play around if you want to. So I would like to just briefly introduce myself and my background. So I am working in geographic information science realm, research and teaching for over 20 years. And my main interest is spatial decision-making models. And I focused on uncertainty and sensitivity analysis in spatial decision-making models for a while, and how to visualize the outputs of uncertainty as well. I teach various courses in various levels of GIS courses, including Intro to GIS, Cartography and Geovisualization, and Spatial Data Science. But today's topic will be much related with this spatial decision making. And before going into deep, so let me just briefly talk about what are the spatial composite indicators, why should we care about them, and how can we improve them? So these might be maybe a new concept for some of you. Might have never heard about spatial composite indicators, but they're actually very well integrated in our everyday lives. And some of you might already have heard about the multi-criteria evaluation, when we have various criteria that need to be evaluated at hand and varying preferences. We always touch about this composite indicators, but however we define them. So, okay, I'm just making sure my Zoom window is not blocking my way. The composite indicators is formed when there's individual indicators, or we can also call them as criterion, are compiled into a single index. And this is a multidimensional concept that we're trying to measure, and it has various components, as I said. So the first characteristics are very simple. So they provide a summary picture of multidimensional complex systems that we're interested in, and it gives us a summary statistics or summary index that we can understand better. And there are various examples, as I said. For example, most famous one is the social vulnerability index. When we singly treat each and every indicator, it's difficult to maybe comprehend all at once. For example, income, race, ethnicity, but how we're going to define the vulnerability becomes the questions, and that difficult multidimensional question is comprehended by the use of these indexes. They are synthetic and performance-based. That means that there isn't such thing called, for example, vulnerability index, but it is made up in order to make a metric to represent this complex phenomena, which is not directly measurable. So you can't literally go ahead and measure the vulnerability, but there are other metrics that help us to measure this index. And they are pseudo-spatial. So even though some of them were derived from spatial data and represented spatially, they do not reflect spatial relationships. So for example, most of them are not spatially aware, and spatial correlation is not considered in most of these composite indicators too. And last but not least, they are subjective in selection. And this is actually leads to why we're going to use machine learning algorithms. What goes into a composite indicator depends on who makes the choice, usually the decision maker. But what is going to be included in that particular index is very subjective. And they're also subjective in weighting. So like, what are the priorities and which parameter is more influential than the other is always a subjective decision. So what can be done differently? Defining these spatial composite indicators. They can be spatially inherited, spatial dependent. They might be policy relevant, and they might be representing the reality better, of course. So the question becomes, what is to do with AI, particularly geo AI, right? Today's session is more about that, like how we can really integrate the machine learning in defining these indicators. And here I would like to just open a parenthesis here and say that, like, I am a supporter of using this type of technologies if we really need to. And now I'm going to hopefully convince you like why it's really important to use these technologies in this particular decision-making context. So if you remember, these spatial composite indicators are simplified. So you are, for example, looking at 150 attributes of the demographics of census data, and it has a lot of useful information about socioeconomic status, household characteristics, racial and ethnicity, and minority status, housing type of transportation, and whatnot. So it is really difficult to just look at this 150 attributes all at once and say what we can include and what need to be included in those indices. So in that sense, the understanding the patterns and reducing this high dimensional data by preserving understanding the patterns that is embedded in this data set is really important. So in order to capture the complex system and relationships, it's really important to just take advantage of the existing technology. And in this sense, I would like to introduce you the technique that I applied. It is called self-organizing maps. And there are special type of neural networks, also known as convolutional neural network, and they are used to explore and visualize the patterns in high-dimensional data sets. It's first introduced by the Cohen, and sometimes known as the Cohen maps as well, and has various applications in the geographic science domain, and it is found to be very effectively applicable to the data sets containing a very large number of observations or dimensions for pattern discovery, exploring relationships, detecting of irregularities in the data sets. And SOM is applied as a dimensional reductional technique is for attribute space in various fields in geography, such as demographic change, street networks, motorcycle flow, or trajectory analysis are some of them. And what is good about the self-organizing map is that it maintains the topological properties of the input space, meaning that the neighboring data points in the input space will be also close to each other in the map. And this property helps visualizing and understanding the relationship between data points. So I would like to just briefly go over like how the self-organizing maps, because I think this will be useful to understand before we go over the notebook itself, how it functions. Let's see how the SOM network works. Any information that passes through this network is tried to be understand by neurons. And during the training process, which is very typical for any machine learning algorithm, individual input vectors that are presented as neuron grids send one at a time, and each time this best matching unit founds and weights of that other neuron vectors and adjusts themselves accordingly. And neurons are modifiable functions, and these functions are possible through the weight. These modifications are possible through the weight. So small adjustments are done and each and every time during the training process. And neighboring neurons are also modified to better fit that specific input vector, which eventually forces the similar input data to be associated with the closely positioned neuron, which enforces the similarity after all. And as I mentioned, topology is an important part of characteristics of the self-organizing maps. Therefore, each neuron in the SOM grid is closely related to each other, and each of the inputs are connected to each output nodes by means of a connecting weight. And we try to find the set of centroids to represent these clusters, but with topological restrictions. So we have our input, and we would like to transfer the data to the output where we can see this relationship better. And one thing to highlight here is in GIS terminology, our features could be a single grid cell, or it could be a single feature, a point, polygon, or line. And every single feature is considered as a vector in self-organizing map lattice. So here I have a small 3x3 example. Hopefully will illustrate like how this functions. And the example is taken from Agarwal and Skupin's book, which I highly recommend if you're interested in the topic. So we start with initializing the SOM lattice, and I will be happy to just talk about these parameters later on, because if you are familiar with any machine learning algorithm, the parameters are really important, especially when you initiate the training. So the initialized SOM lattice is one of them. So the size of the lattice, like how many times that you're going to do the training, or the kernel size, these are the parameters that you have to evaluate in order to get to design number of clusters. And here to just, maybe I can just have my laser pointer here too. We're going to start with a 3x3 input vector. And let's send our first, input vector, which finds its location at x2, 1, y2, x1, y2, sorry about that. And this means that it is finding its best matching unit there. And it's the closest distance, most similar to place that observation 1 looks like. And accordingly, the weights of that node is adjusted immediately as soon as the vector 1 finds its place. So we're seeing the change in the neighborhood cells. So now our vector feels more comfortable in its location, making its neighborhoods also look like its weight. And for the next cycle, we send the second vector, which finds its place in x3, y3 this time. This means it's as different than the first vector that we just sent. And immediately, again, this vector modified its neighbors as well. And when we send a third one, which is more similar to the second one, therefore it's find its location closer to the second one, another change happens in the surrounding neighborhood, but I would like you to notice like what is happening in the very middle. This means that we are starting to see a separation between our clusters because each cluster tried to differentiate itself. So there's a natural boundary occurs in between. And this whole process would be repeated many times, or dealing with the real data as the training progressed. The input vectors may then be reused and find a best matching unit, which is different from the previous cycle. All the examples are set, and we have, I think, one last vector too, which is the fourth one, and find its location too, similar to the first one. So all these adjustment has been done, and weights are recalculated through the training process. So what does this mean in terms of our real spatial cases? So once we have all the data points passed through the square grid we define as the unified lattice, they are matching a feature. And here, for example, you see one completed training. What happens is each cluster has an ID, and we can use these cluster IDs in order to define and link to the real world spatial features, so that each ID assigned to an attribute to each polygon. So we can use this to create a thematic map of the phenomena that we're looking at. And here you're seeing an influence map follows some weighted lattice topology. So what does it mean? The clusters are highlighting among all of these attributes, which is the most influential one. So if we can see that particular attribute, we will have a better understanding of what is the most influential characteristics for that particular cluster, and we can relate this to the spatial unit that we're interested in. And here's an example of a real world, like real application. A small portion of the output, which is easier to understand since we have only 13 categories here. And in this example, the self-organizing map is applied on demographic factors, on flood zones, and in social vulnerability index that has been used by CDC, we are only looking at 16 factors of them, and they are the summary of demographics. And instead of that 16 categories, if we just use the entire set of demographics, like 150 of them, and use the pattern recognition by self-organizing map, then we will see more nuanced differences in certain regions. For example, we can see that some themes that has been summarized under household composition has more nuanced differences in certain flood zones, and this will help us to understand like what are the really most influential factors in that particular location. And these examples are hopefully illustrative, but I would like to also mention like what is the current notebook that resides in the iGuide platform is all about. Currently, I am working, collaborating with my colleagues at Brown who initiated navigating the new Arctic project, convergent pressure on the Arctic development. And that is a huge NSF project with 15 investigators from 10 different institutes. And they are particularly looking at the patterns of human presence and activity in the Arctic, which will strongly influence how the future is shaped. And this is true to a large extent anywhere in the world, but high cost associated with building new settlements and infrastructure in the high north lead to a potential higher than average degree of path dependence in the Arctic. That's why it is important to understand like the dynamics in the Arctic, like what are the influential factors highlighted in certain zones. And in this project, I aim to present a comprehensive approach for enhancing spatial composite indicators through the dimensional reduction capabilities of machine learning. And the use case is the Arctic development, and I have various data sources considered here: socioeconomic, environmental, and infrastructural data sets, which can provide a more holistic perspective on spatial vulnerability and opportunity. And I will explain the data sets briefly in the next slide, but the overall, like all of these data sets are really important, and but which ones are most influential in certain zones are the priority. And currently, I have students who are working on just the original NSF project, I'm sorry, already have a gathered data, and we're trying to refine and enrich that. So I have students who are working on these data sets. They are working on environmental, sociocultural, infrastructure, economic, and political data sets. More on the way, as I said. That is why you won't be seeing a completed data set, unfortunately, in the notebook. And initially, I created just a random data set to just show the methodology. But last week, I tweaked the data set. So hopefully you're going to see some more realistic results today, even though, as I said, it's not 100% finished data set. But I think it will be important to highlight the importance of the study. And I would like to also highlight one thing that like another study that we're doing for the research, which focuses on where does people live, work, visit, or otherwise have interest in this vast and diverse region. This is why it is crucial to see how these data layers are creating an infrastructure and how we're understanding the importance of this data. So this is actually wraps up like what I would like to introduce you as a background of the study. And I would like to pause now and see if anyone has any question before we move to the algorithm.
So yeah, any questions for Seda at this point? So Seda, maybe we'll continue and yeah, with the
Sure. So let me just um mm, wonder what will be the best place to just go over. Do you want me to just show how people can access maybe?
yeah, like if there is kind of a hands-on kind of thing, like if people can access and do it, I think
Yeah.
the notebook is available, right, on the platform. So
Yeah, so let me first I'll just dismiss this slide. Taking my way. Okay. Whoops. Oh no. Okay. So I can open. Okay, so the notebooks, let's go to maybe the main page of iGuide. If you log in to the platform, there are lots of cool things. I hope you are already enjoying. But let me move to the.
and we can search for it as well, Seda. So platform.
Yeah.
And we can search by Seda's name
Okay,
and
yes.
find our notebook as well.
This is the screen that I was trying to find. It's called Rethinking the Spatial Composite Indicators with the Lens of Machine Learning. And when you click that, it will take you a short description, and then there will be a link to the notebook itself. So I think it wouldn't be wrong to say that everything resides in iGuide is connected to a repository, and what I have all of the notebooks and related environmental requirements and example shapefile is residing in the GitHub repo that I just created for iGuide. So whenever I make update in the notebook, hopefully that will be also reflected here, but this doesn't mean that you can't just download and make your own copies or just working on it on your own Jupyter Lab environment. That's also possible. So this version is the correctly hopefully run version. So you will see some outputs of the cell, and I won't be real time running it because it might take longer than the allocated office hour for us, but I will just go over every single cell and explain you what it does. So that means
And
when
for
you
people,
start,
if you want, you could run it by yourself also. Like there is, if Seda, you go up on the top of the page, there is this
here,
run
so
this
yeah,
notebook, which will launch into the Jupyter environment. It will download everything which Seda has,
exactly.
and you can run through
Yeah,
and change it,
exactly. Thanks
do whatever
for
you want to.
chiming in. So as I said, since the environmental requirements are already defined, hopefully you won't have any issues, but let me know if there's anything missing. So here we can go over the from here as well too. The first cell is just making sure that we have the related packages are installed before start working on. And as I said, initially I had just the randomly generated data and then like an example set, but here I put a link to the document that we started creating, the new data sets. And this means that once this is finalized, I will hopefully be able to replace the example data with the original data. One thing I would like to explain here is the data set that we're referring to is various, and some of them are raster, some of them are point line or polygon-based vector data. So what we're trying to do is make sure that we have a single layer and reflecting all these attributes. And in order to have the zonal summaries of this data set, we apply the zonal statistics. So for each zone, we will have the required data set available. And so after having all the necessary packages, the second cell is focusing on bringing the shapefile that I just described. So we are seeing currently the hexagon files or zones for the Arctic region. And all of them has the required information that has been coming. And if you would like to play around with the random data set, here's a short example that you can create. For example, demographics, animal distribution, sea level rise. So you can define any category here and increase the number of attributes for each category. It's up to you. But this is the data set that I put as a shapefile. So this has just 24 columns for the time being, and some of them are educational point files or some other socioeconomic things or pipelines or any thing that might be related to the Arctic development. And once this data set has been included in the notebook, we start with standardizing it. So it will be ready for self-organizing maps. And remember, I mentioned a lot of parameters that goes into self-organizing map. And here is a summary of them. So the size of the unified matrix is something that you need to try and play around for your own case if you would like to modify this. And it could be a square, it could be a rectangle, again, depending on like the output, like what you got in your unified matrix. You'll have to explore various outcomes. And the rule of thumb is it's the length of your like the vector file and taking a square root of it and multiplying it 5. So this might give you a good start of like how many neurons you might need in your unified matrix. And another parameter is the kernel density, like how kernel width, and all of them will end the training epoch too. So all of these parameters will influence you how your clusters end up. So once you have a good set of parameters, you can initiate your training. And this takes the longest time. This is why I don't want to just run this because it might take longer than half an hour or so. But once that is finalized, the remaining will be rather quicker, which is generating the unified metric as we have just seen. And we are starting to observe some clusters in the matrix. And once this is set, after having our clusters and indexes available, the upcoming cells enables us to get those cluster IDs and associate with the features that we have. And here, in the remaining cells, we are doing those conversions. So each cluster ID and a feature is assigned. And in order to do that, we need to have unique feature IDs, obviously. And this is already satisfied for a shape file or any index file. But if you don't, you need to make sure that your features are indexed as well. And we are doing a join operation before specially representing these files. So each feature now have their cluster ID. So this is important if you remember the slide, because we can have that connection from unified matrix to the spatial unit. So for example, here the feature 1 is falling in the cluster 12. And how we're going to visualize this, by using GeoPandas, we will be able to visualize this data set. And I'm just scrolling down a little bit to show you the final result. With this example data set, we can bring the most influential cluster IDs and relate it with to the hexagons that we start with. So this means that after looking at that 24 attributes, the algorithm selects the most influential one and highlights in this cluster. If you have too many clusters, which could be more than 10, I also included an interactive visual, but I think this hasn't been run in that version. I might have it here somewhere. So let me see if this bouquet cell is up and running here. Just scroll down towards the end. Okay, it's loading. Hopefully it will come. In the meantime, I think I have some questions. Okay, yeah, so I included the Minisome in the requirement, but if it might have an issue, but thanks for just pinging that, Anand. Could you post the links again? Okay, I would like to just repeat the links again for the ones who have been asking. This is the platform link. Thank you for staying. Hope you enjoy. Hope, please let me know if you have any questions and if you notice anything, any issue. I hope you will enjoy working on this too. I don't know why it takes so long to bring the bouquet, but it's a very like a fun tool to just run to. So it will just bring you the interactive visual. Okay, and if you have any issue with the bouquet too, I will just repeat the pip install as well. So you might need to just include that too. I might have that in the requirements too, but you never know. Yeah, I might miss that. Yeah. So it might worth to just include the last line that I provided too. Any other questions? Hopefully this wasn't quick or explanatory enough.
I had a quick question.
Sure.
So when you input your data set, you're using like a common geometry, like the hexagons. Is that correct?
Correct. Yes.
Okay. So if we were doing something, say, for like the US and all the data were in county level, would you still go to hexagon or would you still use, or would you go to county since they're all in the same geometries?
You can use any geometry that you like. This is what
Mhm.
actually I would like to just highlight different examples. And I use some for social vulnerability index related attributes, and this is for Arctic attributes. And for the Arctic, we have various data source. And what I wanted to just make sure that everything is summarized in the same unit to make it more representative, because we are looking at a vast area and talking about a lot of different countries in the context of Arctic. But in the United States example, you can use any tabular data and feature combination. So it could be census tracts, United States, states boundaries, counties, whatever you would like to.
I see. Okay.
Just make
And-
sure that you update this, but it should be the rest should be okay. And
Okay.
yeah, and I also here do coordinate reference system check too. So I want to do that too.
I see. And in areas like the Arctic, I imagine there's probably a lot of no data values. How does it do with no data?
Oh, that's a great question. So this is actually why I've been underlining that this is an example data, because it's not just no data, but it's also some sensitive data that we're talking about. So like how we're going to make sure that one area is not overrepresented compared to the other. So this is something that we're still working on. Because in certain parts of the Arctic, we have these kind of issues. So currently the no data is handled as no data, but I'm also working on how we can make sure that data representation is also as homogeneous as possible.
Okay, thank you.
Thank you.
Hi, Shada.
Hi.
Are you doing anything specific to take account of, I mean, you're using cells which are kind of match the smallest unit that you have, I assume, and you just project the results from any data layer into those cells, right? Is that correct?
Can you repeat your question, Andy?
So the hexagonal cells you're using,
Uh-huh.
they're overlaid by a data set, typically a polygon with has set of attributes, and you basically project the attributes for that data set to each cell according to which part of the data set it falls into. Is that right?
Yeah, correct.
Okay. So you're not taking into account the possibility of, for example, uneven distribution of data in
So
the census tract. So census tract, for example, half the population or 80% of the population might be in one half of the census tract. In other words, not necessarily an uneven distribution. Are you taking that into account at all, or are you just go ahead and just doing a uniform distribution of the data?
yeah, that's a good question. So every single attribute might have different distribution, and before putting them into the training, I have a cell that is handling the normalization of each attribute. And this is very typical in a lot of multi-criteria evaluation system. You have to standardize data before combining them or comparing them to one another. And that has been done before the training session.
Okay, so you're normalizing by area or by some other parameter,
Yes.
like a ratio.
Every environmental factor has its own way of, because as you just said, like population can be normalized depending on the total population, and some other stuff could be based on the area. And as I said, there are so many different types of features here that we're talking about. Some of them are points, some of them are lines. We're talking about proximity. Some of them are aerial units, and we also have the raster images too. So that is why there isn't any like a finished version of the data set. We're still fine tuning that, but once it's set, then the algorithm will be ready to be tested.
Okay, that sounds good. Thanks.
Thank you.
Any other questions for Seda? Yeah. So thank you, Seda. I think this was really great.
Thank you.
Yeah.
The pleasure. Yeah, hopefully it will be useful for anyone who would like to test and try. And
Yeah.
please reach out to me if you are working with it. I would be happy to hear your comments and how it goes. I'm curious to see if it will be useful for anyone else too. So
Yeah, I'm sure it would be. And I guess we will post the link to this video as well. So people who are not able to attend will be able to view this as well. So again, thank you, Seda, for doing this.
thank
And
you.
I look forward to learning more from you in the future as well.
Thank you. It's a pleasure.
So that concludes kind of our today's session. Thank you all, and we'll meet you next time. Bye.
Bye.